Hi everyone. In today's video, we're going to continue our discussion on aromatic compounds. This time, we're going to look specifically at the reactions at the benzylic position. We're going to look at reduction of benzene specifically, and then we're going to finish up with spectroscopic considerations where we're looking at benzene-containing compounds. It's my goal that by the end of this video, you'd be able to predict the major products, including stereochemical outcomes, and propose mechanisms for substitution and elimination reactions at the benzylic position of a benzene ring. You would also be able to predict the products and identify suitable reagents for oxidation at the benzylic position, and then you'll be able to predict the major products and identify suitable reagents for the reduction of benzene. There's going to be one specific type of reaction we'll focus on, which is the Birch Reduction. And then lastly, you should be able to predict and interpret IR, H1 NMR, and C-13 NMR spectroscopy involving benzene rings. As a refresher, consider this particular benzene-containing compound. The benzylic position of any compound containing a benzene ring is the position alpha or right next to the benzene ring. And recall that the benzene ring itself is very stable. However, while that benzene ring is stable, the benzylic position of your benzene ring is actually particularly reactive. And it tends to go through a series of reactions from substitution, elimination, oxidation reactions very readily. So we'll begin our discussion with oxidation at that benzylic position. And just to state right up front, even under very strong oxidizing conditions, so using your sodium dichromate salt in acidic solution, benzene rings do not get oxidized. So there is no reaction that is observed if you just take a regular benzene and you treat it with sodium dichromate. Same thing with an alkane, similarly very unreactive towards oxidation in the presence of really strong chromium-based oxidizing agents. However, interestingly enough, if you take a benzene containing compound with an alpha position that is an sp3 carbon, if you treat that benzene ring, if you treat that compound with sodium dichromate in the presence of H2SO4 and water, you actually end up with a complete oxidation of the alpha position. So the alpha carbon gets oxidized all the way to a carboxylic acid, and the rest of the R group gets completely lopped off. So that's important to note that you can actually pretty much remove your R group off your benzene, keeping only that alpha position that gets carboxylated. Alternatively, you can treat that same compound with potassium permanganate, and this time you will get the carboxylate salt, which you then have to protonate in a second synthetic step using H3O+. So note that the oxidation reactions we're describing here works when you have an alkyl substituent with at least one benzylic CH bond. So there needs to be a CH bond at the benzylic position for the oxidation to actually occur. Okay, so now let's go on to free radical bromination. So we've also learned in the past from previous classes that if you take an alkane and you react that with NBS and light, the most substituted carbon with a CH bond will get brominated through a radical chain process. The same thing occurs with a benzene-containing compound, but specifically the alpha position or the benzylic position will be selectively brominated under these conditions. And that's because the radical that you form in this reaction is actually going to be stabilized by the benzene ring. So this is all kind of more of a review from your previous lessons on this particular topic. Okay, so here's a particular kind of free radical bromination that's going to be useful as we move forward in this particular chapter. If you take your toluene, and specifically your toluene with a CH3 group, and you react that with excess of your N-bromosuccinimide in the presence of light, you would end up with an excessive bromination, specifically at that alpha position, once again, at the benzylic position of your benzene ring. So your toluene will get so the CH3 group on your toluene will be converted into a CBr3 group. Okay, so now let's consider substitution reactions at benzylic positions. Okay, so these two reactions should come as no surprise to you. You've learned about substitution in the past. If you take a primary benzylic bromide and you react that with a strong nucleophile, such as your hydroxide, you would form your primary benzylic alcohol as your major product in an SN2 reaction mechanism. If you take a tertiary benzylic bromide and you react that with water, this time you will go through an SN1 pathway, which will then get you to that same tertiary benzylic alcohol in an SN1 process. So this is all review, but just to note that you can do both an SN2 and an SN1 at the benzylic position of your benzylic halide. Okay, and then we're going to go to elimination next. So you can perform elimination reactions fairly readily at the benzylic position of your benzene-containing compounds. So for example, if you take your benzylic alcohol and you treat that with concentrated H2SO4, you would form your alkene as your major product through an E1 process. So the first thing is your alcohol gets protonated, it leaves, you form a carbocation, and you go through a proton transfer. Okay, so just remember that particular reaction. You can also have a benzylic halide, such as a benzylic bromide, and you can treat that with a strong base, and then it would also go through an elimination reaction, this time through an E2 mechanism. Okay, so now let's focus on reduction chemistry. So while you cannot oxidize your benzene ring using even your strongest oxidizing agents that you know, you can indeed reduce your benzene ring. One way you can do this is use your regular old hydrogenation reaction. So you can pump H2 gas in the presence of a metal catalyst into your benzene-containing flask, and you will reduce your benzene ring, but you do need really high temperatures and very extreme pressures. So for example, if you take this benzene ring and you try to react that with your hydrogen gas, you're going to need to put this on the nickel catalyst, for example, and you need to kick up the temperature to 150 degrees Celsius, and the pressure of the container needs to be 100 atmospheres. That is incredibly large. Compare that to standard pressure, which is at 1 atmosphere. This is really, really large of a pressure that you need to subject your reaction to. This is both a good and a bad thing. The bad thing is that this is not going to be a very viable way to synthetically reduce your benzene specifically. But this is good because that means you can actually fine-tune this reaction where you can selectively reduce vinyl groups in the presence of benzene in a particular compound. So for example, take styrene and react that with your hydrogen, this time under a platinum catalyst. If you reduce the pressure to about 2 atmospheres and the temperature to about 25 degrees Celsius, you can selectively hydrogenate your vinyl group and leave your benzene ring completely intact, right? Remember that to reduce the benzene ring under these types of reactions, you're going to have to increase the temperature to a really large temperature and the pressure to incredibly high. So if you can fine tune that, you can actually make this reaction selective for just vinyl groups in your system over the benzene rings. But what if you do want to reduce your benzene ring and do so in a way that's synthetically viable under relatively mild conditions and also very safe conditions as well? Well, you can do so with what we call a Birch reduction. And the Birch reduction reagents look like this. It actually looks a lot like your dissolving metal reduction that we've seen for alkynes going down to alkenes. Take a sodium metal solid and you dissolve that this time in methanol and ammonia. You can treat that benzene under these conditions and you would form your isolated cyclohexadiene. So notice that we've formed two sp3 carbons in between the two vinyl groups that are on that six-membered ring at this point. So this would be an isolated diene. So we will not cover the mechanism for the Birch reduction of your benzene, but there are two important notes that we need to make sure we know when you're talking about regioselectivity of your Birch reduction. So if you're dealing with alkyl benzenes or alkyl substituted benzenes and you treat that under Birch reduction conditions, you will selectively form an isolated diene in which the carbon bearing that alkyl group is not reduced. So specifically, you do not reduce the carbon bearing that alkyl group. So notice that the reduction happens at the off carbons. Secondly, if you're dealing with an electron withdrawing group on your benzene, so such as like a ketone, an aldehyde, an ester, nitriles, all of those types of electron withdrawing groups, now there's also a regioselectivity that is observed in these types of Birch reductions. You would actually selectively reduce the carbon bearing that R group. This time as your major product, it is indeed the carbon bearing that electron withdrawing group that does get selectively reduced as well. So you form an isolated diene that incorporates the reduction at that particular carbon that's bearing that electron withdrawing group. Okay, so now we're going to finish up this video with spectroscopy. So we're going to revisit spectroscopy, but this time think about it in terms of compounds that contain these benzene rings or these aromatic systems in general. So we will start with IR spectroscopy, and we will look specifically at benzene itself, so the parent compound, and try to dissect all the different absorption bands that we would observe in an IR spectra when benzene is present in your compound. Okay, so the first feature that we want to definitely look for when we have benzene-containing compounds is that CsP2H stretch. So we know in general that if you have a CsP2H stretch, you should observe that absorption band between 3000 and 3100 wave numbers per centimeters, and it should have some medium to weak intensity. Another fairly unique feature of benzene is that you do have what we call these combination bands and overtones. So they're usually somewhere between 1 to 4 of these around the 1700 to 2000 wave numbers. And they're very weak in intensity. So sometimes you might actually not see it, but sometimes you do. And so you can get pretty lucky. But this would be pretty weak in intensity, in that particular range. In addition, you would find those CsP2 stretching vibrational modes and the ring vibrations in general at 3 specific wavelengths, so approximately 1450 wave numbers, approximately 1500 wave numbers, and then finally approximately 1600 wave numbers. And then generally, once again, 3 signals that you're going to see at this particular region of your IR spectra, and they would have fairly sort of medium intensity. When it comes to the low frequency vibrational modes, you do see also several signals between 1000 and 1275 wave numbers, which would coincide with your CsP2H bending, so usually the in-plane bending around that particular region of your IR spectrum. There will be several signals and they will be fairly strong. So those CsP2H bending, especially for benzene, are really, really strong. Okay, and then lastly, you would also observe the CsP2H bending, and this time out of plane bending vibrational modes. They're usually somewhere between 690 and 900 wave numbers. This would be like 1 or maybe sometimes 2 signals, but they will also be pretty strong intensity. Okay, so the benzene one is very peculiar because a lot of these features individually can be shared by other types of functional groups. For example, the regular old vinyl group will have 3 of these different vibrational features as well. And so it's important when you're dealing with benzene compounds to look for the combination of these different vibrational modes in your analysis. And so here is an illustration of all the different bands and modes that we've talked about in our on this scene. So notice that between 3000 and 3100, we have those CsP2H stretching modes. So take a look at those combination bands and overtones. So that's pretty clear here, but once again, I want to warn you that it's not always that clear, but you should see some of those tiny spikes. And then between 1450 and 1600, we can see those stretching vibrations and ring vibrations between 1450, 1500, and 1600. And then you can see that you have the CH both in plane and out of plane bending vibrational modes, either between 690 and 900. You have those really strong signals, as well as between 1000 and 1275. Okay, so it's that combination of IR vibrational modes that you should be looking out for compounds that could potentially contain benzene. Okay, so now let's consider the H1 NMR features of compounds that contain benzene. So the unique features of your H1 NMR spectra for compounds containing benzene rings is really all coming from anisotropic effects. And recall that anisotropic effect is caused by induced magnetic fields caused by pi electrons moving in a current. So think about your benzene ring. There's a secular current of electron density around above and below that ring, and that would actually cause an induced magnetic field. So if a proton is placed in a location where the direction of your induced field is in the same direction as your magnetic field, there will be a further de-shielding effect of those protons, and it will shift the proton chemical shift downfield. So the protons around a benzene ring on the periphery of a benzene ring are significantly de-shielded due to that induced field in the same direction as the applied magnetic field B naught. And so you should usually would see these protons way further than regular old vinylic protons, somewhere in the 7 parts per million region. So if you take this particular compound, ethylbenzene, I want to determine, we want to predict the HNMR chemical shift for the different types of protons on here. We will see that all 5 of those protons directly on the benzene ring are going to be somewhere around that 7 parts per million region on your H1 NMR spectrum. And they, because of how close they are all together, they're going to look like a multiplet. You're going to kind of see almost like a bunch of lines at that 7 parts per million region. And then your benzylic protons are also going to be shifted downfield due to anisotropic effects, not as much as your protons directly on your benzene ring, but still pretty significant. So even your methylene protons that are on that benzylic position are going to be shifted to 2.5 parts per million. That's up from 1.2 parts per million that you would have predicted it to be. And then your methyl protons that are beta away from the benzene ring, those are not significantly shifted downfield. So anisotropic effect only really occurs at the protons directly connected to the aromatic ring, as well as the benzylic protons. But once you get further down from that, those effects are reduced dramatically. So that's for sort of monosubstituted benzenes. But for disubstituted benzenes, you do get some interesting unique features at that aromatic region on the H1 NMR spectrum that can be pretty helpful when you're trying to figure out substitution patterns on your molecule. So here, what I've done, I've shown you are 2 different types of disubstituted benzenes, but specifically just looking at para-substituted benzenes. You can either have it where both of them, so both of the X's, for example, are identical, and so you would have sort of identical protons on that benzene ring. Another option is if you have that para-substituted benzene, but this time there are 2 different substituents, X and Y, which means that you would only really have anisotropic protons, and so there'll be 2 different signals that you should observe on that benzene ring. So in the first case, you would have essentially 1 signal around 7 parts per million, and it would pretty much be a singlet. The second case is a little bit more telling. You basically get 2 doublets in that region. So that's actually a very important marker and a signal for you as well. Whenever you see 2 doublets at the benzene region or the aromatic region of your H1 NMR spectrum, that's typically telling you, that's a very strong indication that you have a para-substituted benzene in which those 2 substituents are 2 different groups. So just keep that in mind as you're kind of thinking about your H1 NMR analysis. They're really cool features that you can use to very quickly get at your answer. Okay, so lastly, when it comes to C-13 NMR, the key thing to remember is that benzene carbons end up showing up at the 100 to 150 parts per million region in your C-13 NMR spectrum. What's really helpful in your benzene C-13 NMR is that it is very helpful in telling you about substitution patterns in your benzene ring. Okay, so here are a series of disubstituted benzene rings with different types of patterns, which will result in different types of signals and different number of signals in your C-13 NMR. So let's start with the 2-signal case. So once again, if you have a disubstituted benzene that's para-substituted, and the 2 substituents are the same, it would turn out that you would end up with two different carbon signals between the 100 and 150 range on your C-13 NMR. So if we draw those two lines of symmetry on your benzene, one may then see that in reality, there's really only two different kinds of carbons on this benzene. You have the carbon that bears that substituent X, and then the carbon ortho to that carbon bearing the substituent X. So those two carbons are going to be different, but every other carbon on this ring is equivalent to one of these two. So you should see two different signals on your carbon 13 NMR. In the ortho-substituted case, where the two substituents are identical, there is both an axis and a plane of symmetry that is bisecting the two substituents, which means that there are only three unique carbons on that ring, and so three unique carbon signals will be on that on that C-13 NMR. In the examples where you have four signals, what I have done is to draw out both the axis and the plane of symmetry that you can use to determine the number of unique carbons in your C-13 NMR. In the first case, all four carbons on one side of that axis and plane of symmetry are unique. The same for the second, and the same for the third, right? So once again, if you find that line of symmetry that helps you see the mirror plane or the axis of symmetry, that would help you figure out all the unique carbons on your C-13 NMR for your benzene ring. And then lastly, in the case with six signals, there's actually no axis or no plane of symmetry on this benzene ring. And so every single carbon is going to be unique. And so you should expect six signals on there. So once again, this is really interesting. If you know your C-13 NMR for your benzene ring, you can actually start to figure out exactly what kind of substituent pattern you are observing on your benzene ring, whether it's like ortho, meta, para, di, mono, substituted benzene rings. Okay, so it's my hope that you should have seen all these different reactions at the benzylic position of your benzene ring. If you were to do substitution, eliminations, oxidation reactions, you've also been exposed to the Birch reduction as well as your IR, H1 NMR, and C-13 NMR for benzene rings. Thanks so much for watching this video, and I will see you in class.